All right, what I want to do today is actually construct a box plot from data by hand so you can see sort of all the steps that need to be taken. In front of you, you have a data set that's measuring the percentage of cotton in material from some samples taken from the Haynes Corporation in North Carolina. There were 18 samples that were taken, and these are the percentages of cotton in those 18 items from the sample. So the first thing you need to do to construct the box plot is to find the median. And the median, because n is an even number, the median will be the average of the two middle values. So the median is 34.5 plus 34.2. It doesn't matter the order in which you do that because it's addition. And I'm going to divide by 2, which gives me a median of 34.35. Okay, so that's one piece of information that we need to have, which 34.35 of course lies right in there. There's the median. Okay, the other thing you have to compute is the first quartile, and the first quartile is 0.25 times 18 plus 1, and 0.5 times 18 plus 1 is 0.25 times 19, which happens to be 4.75, and we're going to round that to 5. And if we go up here to the fifth data point, we see that the fifth data point is 33.6. So 33.6 is the first quartile. If we go here to the third quartile, we do that by doing 0.75 times 18 plus 1, and that happens to be 0.75 times 19, which is 14.25, which rounds to the 14th spot in position. So find the 14th data spot. And it happens to be the 0.0 as the other part. Those three numbers, I'm going to construct the box plot over here on the right. Those three numbers are used. So when you construct your box plot, the first thing you do is you mark the median, and then you also mark the third quartile. Since it's higher, we go in ascending order, which is 35.0, and then the first quartile, which is 33.6. So actually what happens there, those three things create your box that are in the box plot or the box and whiskers. Again, this is quartile 3, this is the median, and this is quartile 1. So those three things are there. The next thing that's required for you to compute inside a box plot is the interquartile range. So that's the IQR, which is referred to in your textbook. And the interquartile range is Q3 minus Q1. It's just the length in between Q3 and Q1 of the data points. So that, of course, is 35.0 minus 33.6, which is 1.4. So this number is used in order to help figure out the length of the whiskers in the box plot. Okay, so what we need to do now is to create these sort of the whiskers that come out. Okay, so what we do now is we take the third quartile and we add to it 1.5 times the inner quartile range. And I didn't make that 1.5 up. It's a definition of how you create a box plot. So it's always set at 1.5. And that Q3 happens to be the 35. And then we do plus 1.5 times 1.4 that we just found. And if you add those, you get 35 plus 2.1, and that is 37.1. So if you go up to your plot, what that means is you come up here and you draw a little whisker to there, and this is the 37.1. What you should notice is that 37.1 is nowhere in our data set. So our data is actually pretty tight in there because it's not outside 1.5 times the inner quartile range. You also do it to find the other side of the whisker. You do quartile 1 and you subtract off 1.5, the inner quartile range. And again, those are formulaic, so the 1.5 never changes. We always want 1.5 times that inner quartile range, because we're going to define our outliers as anything that lies outside of that. So if we have 33.6 and we're going to take away the 1.5 times the 1.4, which is the 33.6 minus 2.1, and that value is 31.5. So we draw our other whisker down here to 31.5. And so this graph that I put on the side happens to be the box plot, or the box and whisker. Now, what's really important is that in the box and whisker, if a data point lies outside of that, we would have an outlier or an outlier. We can see that we don't have any data points above 37.1. Our highest is 36.3, and we don't have any data points below 31.5 because our lowest is 32.5. So we can conclude here we have no outliers. And that, my friends, is a woohoo, because outliers cause us troubles. So I wanted to do that example drawing a box and whisker. What I'm also going to do kind of in the same lecture here is break it up into using that same data set of the percentage of cotton, and I want to talk about a stem and leaf plot. Okay, so that stem and leaf plot, you typically break it into a class, which is, or what we call the stem, and then we break it into a leaf. And it's just another way to organize your data so that you can see things. Okay, now here's the deal. I'm going to do the tens and ones as my stem. So 32, 33, 34, 35, and 36. So where did I get those values? If you go back to the previous sheet, it's just the beginnings of all those data points. And then on the other side, I'm going to put the decimals. So I happen to have 32.5 as a data point, 33.1, 33.4, 33.6, another 33.6, and I had a 33.8. I had a 34.1, a 32.2, another 34.2, 0.5, and then 34.7. So I'm listing every data point. It's just a different way to organize it. I had a 35.0, a 35.4, and a 35.6. And then I have a 36.2 and a 36.3. Okay, now with that stem and leaf, I can turn this into sort of a frequency chart. So I'm going to then take this and turn it into a frequency distribution, which we have done before. So if I have my interval, and then my frequencies. The stem and leaf plot makes it really easy to break it into trying to lower the screen here, to break it into the intervals. So my interval is going to go from 32 to 33, and then I'm basically going to go from 33 to 34, and then the 34 to 35, and then the 35 to the 36, and then the 36 to 37. So this is another way to get your intervals. You can just get your intervals of your frequency chart from your stem and leaf. Remember previously we did it as pre-described intervals, like a grade A, B, C, D, F, and those have pre-described intervals. Or we did it where we created our interval length because we wanted those intervals to be even. Here they're already even. The thing is you have to decide which one you're going to be inclusive with. So I'm always going to be inclusive with this one. So just so you know. So I'll explain that in just a minute, the language that I'm using. Okay, so between 32 and 33, I have 1, right, marking the frequency. So how many do I see? I see 1 number there. If I go between 33 and 34, I have 1, 2, 3, 4. I have 5 values that lie in that interval. I have 1, 2, 3, 4, 5, 6, 7 that lie in that interval. I have 3 within that interval. Notice this one does include 35.0, not here. So be very careful about that. You can decide that when you create your own frequency histograms on your own. I will tell you when I want it to be inclusive on any kind of test or something like that. Okay, so here's my frequency. So if we go here to, I'm kind of running out of room, but I'm going to squeeze it all in here. So if I go to my histogram, so right now I'm doing my histogram. Trying to tie it all together here. Okay, so if I go to my histogram, of course I have my intervals. I'm going to start at 32, then I'm going to go to 33, and I go 34, 35, 36, and 37. And then here on my y-axis, of course, is my frequency. So if I go 1, 2, 3, 4, 5, 6, 7, here's 7. Here's 1. Okay, so I'm just doing my frequencies. If I go from 32 to 33, I get 1. If I go from 33 to 34, I get 5. 34 to 35, I get 7. 35 to 36, I get 3. And between 36 and 37, I have 2. Okay, so that's kind of what my histogram looks like. And you could, of course, draw a little bit of picture about it to see. It does, in my opinion, look a little skew right. If you look here and you mark kind of all the previous data points we found, remember that the median was 35, so right here is the median. If you happen to find X bar, just because, I don't know, you don't have anything else to do and you want to find X bar is 32.55, and 32.55 happens to be here. So X bar is less than the median. Okay, that should have a little bit of like ding, 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 ding. I'm trying to point something out right here. So if we take I'm going to take 3 drawings here of like underlying histograms, right? Imagine histograms. Again, this is where the tail is, so skew right. This is where the tail is, so this one is skew left, and this one happens to be symmetric, right? There's some things. In a skew right situation, X bar is less than x tilde. In a skew left, x bar is greater than the median. And in a symmetric distribution, x bar equals the median. So from just that, you can make conclusions as to whether or not something is skewed right, skewed left, or symmetric just by comparing the median and the mean in a data set. It's pretty clever, right? We like this. Two numbers and we can make some conclusions. So that's a good thing. I will have another lecture later.